Hey guys, so conservation of momentum, or momentum in one dimension, is going to be today's lesson. It builds on what we talked about yesterday, the idea of the impulse and momentum, what momentum, the quantity of motion, found by multiplying the mass times the velocity. So the most important thing about momentum is it's always conserved. Whenever you have multiple objects, the total momentum of a system stays the same. So if you think of two pool balls hitting each other and then bouncing away, the total momentum before they hit each other always equals the total momentum after they hit each other. And that's really cool because they're a vector, which means that you can understand the speed and the direction, so the velocity. You actually understand the velocity of things before and after collisions, and you can use that to predict what's going to happen. So, if there's no external force acting on an object, or a system of objects, so if you think back to our systems lesson, if there wasn't any gravity, if there was no force acting on those two pendulums, their total momentum would actually stay the same. So if you got the two pendulums, the two blocks on a pulley moving, they would actually, the momentum of that system would actually stay exactly the same unless you exerted an external force. So if you have things coming in and hitting each other with no force other than them hitting each other, then the total momentum of the system is going to actually stay zero. So it's always going to be the same. The momentum before is going to equal the momentum after. So if there's no net force, then the change in momentum is going to equal zero. So the momentum before the collision, the total momentum of all the objects, and that can be from one object to millions of objects in that system, is going to equal the total momentum of all the objects after. So that's, like I said, that's true for everything from billiard balls to gas molecules. We might have billions of them. In fact, gas laws you learn in chemistry are just an expansion of this, where you take the number of objects to ridiculously huge amounts. So what does it mean? Well, if you measure the momentum of two objects before a collision by multiplying the mass times the velocity and then adding them together, so add the momentum of this ball plus the momentum of this ball, during the collision, if there's no external force, the momentum is going to be exactly the same. And after the collision, the mass times its final velocity plus the mass times its final velocity is still going to be the same. So the momentum isn't going to change just because the velocities will change, but the total momentum is actually going to stay the same. So visually, before the collision, we have a momentum and a momentum. Afterwards, we have a momentum after. By the way, we're going to start using this term prime, and the reason we use prime again is because we have two objects, so we can't use row 1 and row 2, and use row 2 for after, because row 2 is the momentum of this one before. So row 2 is the momentum of object 2, because we have a second object. So what we do is we put a prime after, which is, so row 1 prime would be the momentum of ball 1 after, row 2 prime would be the momentum of ball 2 after the collision. So mathematically, what does it look like? Well, we know the total momentum before the collision is the momentum of ball 1 plus the momentum of ball 2, m1 v1 plus m2 v2. The momentum after is m1 v1 prime plus m2 v2 prime, and that's row prime. But since they're the same, that means m1 v1 plus m2 v2 is m1 v1 prime plus m2 v2 prime. There's an equation that connects all the velocities before and after your collision. By the way, this is also how we prove Newton's third. Again, apology for the squares, I can't get rid of them. If we take that equation and rearrange it to take a common factor of m1 and m2, and then divide both sides by t, because you can do that, because you're not changing the equation, you'll actually notice you get minus m1a1 is m2a2, but ma is just the force, right? So minus the force from object 1 is the force from object 2. That's why when you get a collision, every action there's an equal and opposite reaction. This is actually how Newton found his third law, that the forces actually have to be equal for momentum to be conserved when they hit each other. All right, so what does a question look like? Well, so let's say you've got a honeybee on a stick and a popsicle stick on the water. So there's no external forces. The honeybee lands on the stick, sits at rest for a moment, and then runs to the opposite end. Now, what's going to happen? Well, the bee's going to go this way, but the stick is also going to go backwards as well for the momentum to be conserved. The stick's going to move, just like when if you ever walk on a dock or something that's not secured, you'll actually notice it moves backwards as you move forward. Really funny example of this, I wish I had a video of, was my wife on a dock before it had been secured, and it started drifting out into the lake. And it was interesting because every time she walked one way, the dock would move the other way. So it was actually impossible for her to move because her mass and the dock's mass, because it was a light floating dock, were reasonably the same. So as she walked one way, the dock went the other way. Mathematically, we could figure out how this works. So, by the way, you do not need to convert the masses to kilogram or the velocities to meters per second as long as they're the same, okay? As long as you're staying with kilometers per hour or meters per second or centimeters per second on both sides, as long as you're staying with kilograms on either side or grams, you're fine, okay? Because the units will actually cancel out. So, total momentum is total momentum after he starts walking. So the bee starts walking. The whole problem with these is keeping track of what everything is. So this is where it's really important to write out what you know. M1, the mass of the bee. V1, 0. V1 prime, that we're trying to find. M2, mass of the popsicle stick. V2, 0. V2 prime, the popsicle stick is now moving at 0.120 centimeters per second. So we're saying the bee is positive. That means the popsicle stick is going to be negative. So we're going to make that a negative. Total momentum is total momentum prime. By the way, I would like you either, when you write for the point for writing the equation, the mark, either write this or write that. I want to see one of these two lines before you start plugging in numbers, okay? Because that tells me that by conservation of momentum, what I'm going to be writing actually makes sense. Then it's just plugging in and solving for the one thing you don't know. So the velocity of the bee is 3.8 centimeters per second. Why is the velocity of the bee so much bigger than the velocity of the popsicle stick? Well, the bee is much, much lighter than the popsicle stick is by, by over a factor of 10. All right, another question. And this is basically, for the ADHS people, it's a football question. On a touchdown attempt, you got a 95 kilogram running back running at 3.75 meters per second and 111 kilogram linebacker moving at 4.1 meters per second. By the way, that's negative because we have to pick a positive and negative direction. So we'll pick the running back as being positive, the linebacker as being negative. So here's the question. Does he break the plane? Well, there are two things to note. One is because there's different directions, we have to make one direction negative. Secondly, you don't need to use 1 and 2 as the subscripts if you don't want. You can use whatever you want as subscripts. They are literally just to keep your life easy. So you could actually say, MRB for mass of running back and VRB for velocity of running back, MLB for mass of linebacker, okay? So you can use whatever subscripts you want that make more sense to you. Again, the trick is just writing out what you know. Mass of the running back, velocity of the running back, mass of the linebacker, initial velocity of the linebacker. And then we make that negative. Now, if they stick together in a tackle, here's the trick. We write it out, plug in what we know, but we know that if they stick together afterwards, they must have the same velocity. We're actually going to call this a totally inelastic collision. So after there's a tackle, if they've tackled, they have to be moving at the same speed, otherwise they wouldn't stay together. So we know the velocity of the running back and the velocity of the linebacker are going to, after the collision, are going to be the same. So we could take a common factor, add the masses, solve, and we get minus 0.48 meters per second forward or 4.8 meters per second backwards. What does that mean? Well, I said this is my forward direction, this is my backwards. It means the halfback doesn't make it into the end zone. But again, it's literally just writing out your conservation of momentum, finding the total momentum before, total momentum after, plugging in the numbers, and it's all just adding and multiplying. So the math isn't that hard. The tricky part is keeping track of all the numbers in all the directions. If you make a mistake 90% of the time, you've actually just forgotten a direction. All right, let's say you got someone gliding on a skateboard. So someone's gliding on a skateboard at 4 meters per second and jumps backward off the skateboard, kicking the skateboard forward at 8 meters per second. How fast is he going when he hits the ground? Is he going forward or backward? The nice thing about this is you don't need to know beforehand if he's going forward or backward. The math will basically tell you. You just need to plug it all in. Mass of Tommy, 85. Mass of the skateboard, 5. Initial velocity of Tommy, 4 meters per second. Initial velocity of the skateboard, 4 meters because they're traveling together. Final velocity of Tommy, we want to know. Final velocity of skateboard is 8. Total momentum before equals total momentum after. So mass of Tommy times his velocity plus the mass of the skateboard must be his mass times his velocity plus the mass of the skateboard times the velocity of the skateboard after. Plug in all the numbers. Make sure you keep the direction. All the directions are forward, so everything's going to be positive. We figure it out. Plug in the numbers, do some adding and subtracting, and you get the final velocity is 3.7 meters per second forward. So the only trick with this, once you've written out your equation, make sure you keep everything straight, plug it all in, make sure you take into account of the directions, and you get the right answer. Okay, these are not really hard questions. Hopefully you have good luck doing the worksheet.